Hi there, Bio30s. All right, so today's lesson is going to be about breathing. How does breathing occur? How is it regulated? And a bit about lung volumes. Now, before we start, I just want to make a bit of a correction in the last lesson. So last time we were talking about lungs and the structure of the pleural cavity here. Okay? All right, so I just want to make a bit of a correction here. I noticed in my notes here, I've got a bit of a typo. So instead of pulmonary pleura, this should say visceral. So the term pulmonary pleura can be used to describe the membranes together. Parietal pleura is the outside membrane, visceral pleura is the inside membrane that attaches directly to the lungs. Okay, so on to breathing. How does breathing work? Last lesson I talked about lungs, and we know that lungs are really just an elastic organ. They work in response to muscles. Now, first off, why do we breathe? We also mentioned in our gas exchange lesson that diffusion is passive. So the movement of gases, oxygen and carbon dioxide, occurs through passive transport, which means it has to work off of concentration of these gases. Now, if we just allowed diffusion to take place at its natural pace, this would be way too slow to supply our cells with all the necessary oxygen and to get rid of carbon dioxide fast enough. So that's where we need to have a bit of a forced breathing in order to kind of speed up this gas exchange process with the environment. Okay, so I mentioned that breathing needs muscles. The two muscles that are involved are the diaphragm and the intercostal muscles. So the diaphragm here sits at the base of the thoracic cavity. It's a very large, kind of flat dome-shaped muscle. And then we have the intercostals, which are in between our ribs. Those two are considered our respiratory muscles. When they contract and relax, this creates changes in pressure that allow for inhalation and exhalation. All right, this picture might be useful to come back to later if you want. All right, we're going to focus here on inhalation. Now, it's important to know breathing in and breathing out really works on air pressure. Just like with diffusion, air wants to move from an area of high pressure towards an area of low pressure. So by changing the volume of the thoracic cavity, we can influence the pressure. So pressure itself is also about force divided by area. When you increase the area that particles or objects have, you naturally decrease their pressure, and vice versa. So starting here with inhalation. Breathing in is an active process, which means muscles contract during this time. So the diaphragm is going to contract, and when it does, it moves down, right? The muscle fibers actually shorten, which causes the diaphragm to kind of flatten out and move down. The intercostal muscles contract, which causes the ribs to move out and kind of consequently up a little bit, which increases the thoracic cavity. So the intercostals move out and up. What this does is kind of increases the space that the lungs kind of have. It increases their volume. Remember, through the parietal pleura, they are attached to the ribs, and then the visceral pleura is attached to the lungs, so it kind of moves with it. By increasing the volume of the chest cavity, or increasing kind of the area, we have consequently decreased the pressure inside the lungs. What that means then is that the pressure in the air is going to be higher, and naturally the air is going to want to rush into the lungs from high to low pressure. So again, that pressure differential is created by increasing the volume of the thoracic cavity. Okay? All right, now breathing out is going to be the opposite process. For breathing out, this is a kind of passive or relaxed process. So now the diaphragm is going to relax, and when it does, it returns upwards to its dome shape. The intercostals relax, which means that the ribs kind of return back to their location, and this decreases the size of the thoracic cavity. When we decrease the size of the thoracic cavity, we increase the pressure in the lungs, which in relation to the outside air would be higher pressure than the outside air, and air will naturally rush out from high to low pressure. So again, this is accomplished by relaxing, decreasing the thoracic cavity volume, and air rushes out. Okay. All right. Moving on then to some lung capacity. It's important to be familiar with these few terms here. So when we're talking about lung capacity, we're essentially talking about amount of air that can be in our lungs. But this kind of depends on how you're breathing. So first we're going to talk about tidal volume. Tidal volume is the volume your lungs have during normal, restful breathing. Okay, so when you're not having to actively contract muscles and it just happens naturally. This is typically going to be on average 500 milliliters. That's about the amount that our lungs breathe in and out during a relaxed breath. Then we also have what is known as our inspiratory reserve volume. This means that you could actually forcibly inhale beyond a normal relaxed breath, which we all know we are capable of doing. Expiratory reserve volume is that extra exhale volume you have. So again, beyond your normal exhale, you could forcibly push out more air. If you add all three of these up together then, so the restful breath, the forced inhale, the forced exhale, you get what is known as your vital capacity. That's going to be the sum of all three of those volumes, which means it's the maximum air that you could inhale and forcibly exhale. And typically the average vital capacity is between 3 to 5 liters. Let's take a look at this graph here. All right, which pen do I want? Okay, so this small section right in here, that's your tidal volume. So again, in a normal restful breath, we're only inhaling and exhaling about 500 milliliters. This here is your inspiratory reserve. So you could forcibly inhale that amount of air. Expiratory reserve is down here. You could forcibly exhale, and the vital capacity is all three of those together. We're then left with this other space here, your residual volume. There's some air in our lungs that you're never going to be able to force out, all right? And that is going to be your residual volume left over. All right, so how do we come up with these numbers? How do we measure them? So doctors will actually use a device called a spirometer. Now the spirometer is over here. It's a device that you would breathe into and out of, and it would be connected to a computer to help measure your lung volumes. So doctors would use this to try and diagnose things like COPD or asthma or just, failed lung problems. So basically they would secure your nose or clip your nose so that air is not going in or out there. And then you're going to be taking a full breath in, sealing your lips around the device, and forcing out as much air as possible. And you'll repeat that, and it will help them determine essentially your lung volume. How much air are you able to breathe in and out, and try and get an idea of your vital capacity. Okay, now we're going to talk about regulating breathing. So think again back to our unit on homeostasis about maintaining a balanced internal environment. Part of that is maintaining appropriate levels of oxygen and carbon dioxide. So our body has to be able to respond to either increase or decrease our breathing rate depending on if we need more oxygen or if our body has too much carbon dioxide, or if we're exercising and our body needs more oxygen, things like that. So our breathing is also controlled by a negative feedback mechanism, which means it has receptors, a control center, and effectors which respond to the change. So we'll talk about that right now. Okay, in terms of controlling breathing, if you've noticed going about your day, you don't really have to think about breathing. It happens involuntarily, which means you can do breathing while you're asleep, while you're unconscious. So this is kind of a protective mechanism because we can't really go very long without breathing. Now, of course, we can override our involuntary mechanisms and we can, hold our breath, but eventually our involuntary mechanisms are going to kick in to try and allow us to breathe, okay? So typically, normal respiration rate is about 12 to 18 breaths per minute. That's typical, but obviously that's going to change with exercise, things like that. Okay, so the control center. The control center is the medulla oblongata. This is a section in our brainstem right here. And that's going to be the control center of this negative feedback center, okay? It is then connected to our diaphragm and our intercostal muscles through nerves, motor neurons. The medulla oblongata also acts as the receptor. It has chemoreceptors built into it that sense and monitor carbon dioxide and hydrogen ion or acidic levels. So when we're actually talking about control of breathing, there's kind of two sensor systems. One is going to be responding to carbon dioxide, and the other is going to be sensing oxygen levels. Now, actually, our body is more sensitive to the buildup of carbon dioxide. So if carbon dioxide is building up in our body, that's a waste, that's a toxin. That's going to trigger our body to breathe faster and more to get rid of it. Now, the backup mechanism is then going to respond to oxygen. So if our oxygen levels are low, the backup will kick in. But it's actually kind of counterintuitive to think that our body is actually more sensitive to carbon dioxide. So we know that if our activity increases and our cellular respiration is increasing, we are getting a buildup of carbon dioxide. Now in our body, carbon dioxide will actually kind of create a carbonic acid, and that carbonic acid is going to ionize and leave this hydrogen ion. So our body is sensitive to carbon dioxide as well as that hydrogen ion, and that's going to stimulate faster breathing. So how this works is that concentration of the hydrogen ion and the carbon dioxide is sensed by receptors in the medulla oblongata. So that part of our brain senses the increase of that hydrogen and carbon dioxide. It then sends nervous system impulses to the effector of our muscles, those being the diaphragm and the intercostals. That's the effector of this system. They will then trigger an increased breathing rate. And as the carbon dioxide and hydrogen ion levels drop, those receptors are inactivated. The nervous system impulses to the respiratory muscles will decrease and our rate will fall back to resting. Okay. Now, like I said before, there's a backup that is responsible for detecting oxygen. So there's actually also another set of receptors, chemoreceptors, in the carotid and aortic arteries. So those are kind of just around our heart. They are going to be sensing oxygen levels in the blood. So if those are too low, neurons are going to send that signal to the medulla oblongata as well, acting as the control center. The medulla oblongata will send nervous system impulses back to the diaphragm and intercostals, tell them to speed up breathing. When the oxygen levels return to normal, breathing rate will return to more normal. Okay, so we can kind of just see a little bit of the connection of the nervous system impulses relaying between the medulla oblongata, the muscles, and as well as those chemoreceptors in our heart or around our heart. Okay, that's everything for now. So I want you to actually continue in your workbook. You're going to be working on, I believe it's questions 9 through 14. And you can also feel free to check out a few more videos on my Weebly. It would be videos 4 through 6. All right, thanks for watching.